Hey guys, so today I'm going to be going over some practice problems I put together that will help you guys prepare for your second exam. I apologize, the video that I took during the original study session ended up just saving as a audio file. So redoing the video here so you guys can have access to all of the information that we went over. So second exam is going to cover chapter 4, which deals with alkanes and cycloalkanes and all the properties that are associated with them. Chapter 5 is all about isomers. Chapter 6, chemical reactivity, so kind of some of the kinetic and thermodynamic principles associated with this course. And then chapter 10 deals with radical reactions. Okay, so the first question we're going to go over is nomenclature. So you're asked to provide an appropriate IUPAC name for the following 3 compounds. So when you're coming up with a name for a compound, you first want to identify the parent chain, identify and name the substituents, number the parent chain, and assign a locant to each substituent. And then you want to arrange the substituents alphabetically to come up with your final name. And note that molecule C is actually a bicyclic compound, so that one will require a little bit of special attention. Okay, so first task is identifying the parent chain. In the first compound, the longest carbon chain is 10 carbons long. And so when you begin numbering, you're going to begin numbering from here. And the reason why is because that will provide this molecule with the maximum amount of substituents. If you were to begin numbering from this carbon, you would have 3 substituents, 2 isopropyl groups, and a methyl group. Whereas if you begin numbering from this carbon here, you will have 4 substituents. You'll have 2 methyl groups, an ethyl group, and an isopropyl group. So once you number the parent chain, then you're going to identify all of the substituents. So like I said, you have a methyl group here, you have an ethyl group here, another methyl at carbon 4, and then an isopropyl group. So then when you arrange all of these substituents alphabetically to form a name, you'll get 3 ethyl, 6 isopropyl, 2,4-dimethyl decane. Okay, for the second molecule, you're given this Newman projection. And first glance, this could be kind of a little bit tricky when you're asked to provide a name for this molecule. So the first thing that you're going to want to do is obviously convert this Newman projection into a bond line format in order to come up with a name. And so that's what I've done here. And when you do that, you kind of get something a little bit less intimidating. You realize you just have a cyclohexane molecule with a single methyl group, which would give you methyl cyclohexane or 1-methyl cyclohexane. Now, the last molecule here is a bicyclic compound. You have this cyclic structure that has 3 carbons, and then you have this cyclic structure that just has a single carbon. And when you're coming up with a name for this molecule, you first want to number the carbon skeleton starting from the bridgehead. So you've got 2 bridgeheads here. And you're going to want to go along the cyclic structure that has the most carbon. So in this case, that would be this side. This one has 3 carbons. And so you also want to begin numbering from the bridgehead that will allow these substituents to have the lowest possible number. So if you begin numbering here, that'll be 2-methyl, whereas if you started on the other side, it would be 3-sec-butyl 4-methyl. So 1, 2, 3, 4, 5, 6. So it's going to be a hexane. And like I said, you've got a methyl group here on carbon number 2, and then you've got this sec-butyl group here on carbon number 3. Now the sec-butyl group, it's kind of tricky. A lot of times you'll see it kind of drawn like that. But essentially what happened is you just had this carbon rotate outwards. So you've got 3 sec-butyl, 2 methyl bicyclo, 3,1,0 hexane. Notice that sec, the prefix, is actually not included in the alphabetical naming of the molecule. So the reason why that substituent is named first is because of the B for butyl. And then also note that it's 3,1,0 because the cyclic structure A here has 3 carbons, whereas C only has 1 carbon. A lot of bicyclic compounds will actually have 3 cyclic structures, which is why this nomenclature here provides a space for 3 different structures, so 3,1,0. Okay, second question. Determine whether the following pairs of compounds are identical, whether they're constitutional isomers or stereoisomers. Okay, so the first thing you're going to want to do for A here is convert this Newman projection into a bond line format. And when you do that, you'll get something like this. Then from here, the best thing is to actually then put this in a chair conformation. And then I'm going to actually do a ring flip in order to get these substituents in the exact same location as the second molecule here. Okay, now what we're comparing is this molecule here with this molecule here. In this case, you'll notice that you have the same substituents located on the same exact part of the molecule, but there's different spatial arrangement. This methyl group here is going down, it's axial, that's equatorial, whereas this methyl group here would actually be in the axial position. So these are stereoisomers. Okay. The next pair of molecules, again, are drawn in the Newman projection format. And so what I did was converted those to a bond line format. And then you're kind of comparing the molecules, and they kind of do look a little bit different. However, you really take a look at it, you realize that if you were to rotate these carbons outwards, you would have actually the exact same molecule. So these are the same molecule. Same amount of carbons, same amount of hydrogens, same connectivity, same spatial arrangement, so they're the same compound. Okay, for C, this one's kind of easy. You really don't have to draw anything out. Notice that you've got methyl groups on the opposite side of the molecule, whereas the second molecule here has 2 methyl groups on the same side. So these guys have the same molecular formula. If you were to count it up, you'd have the same amount of carbons, same amount of hydrogens, and you have the same exact connectivity on the molecule, but again, you have different spatial arrangement. So these guys would be stereoisomers. Okay, for D, again, you have these Newman projections. So if you convert this Newman projection to bond line, you realize you have the same amount of carbons and the same amount of hydrogens, but you have a different connectivity. So that makes them constitutional isomers. Okay, so question 3. All of the following compounds are representatives of 2-methylpentane except. So what you're going to want to do is convert these Newman projections into a bond line format and then go through the IUPAC naming procedure to come up with a name for each one of these so that you can compare. Okay, so the first compound here, A, you notice the parent chain has 5 carbons and it has a methyl group coming off of the second carbon. So that makes this 2-methyl pentane. Okay. Second one here, notice that all 3 of these hydrogens are on the backside of the molecule. So that's just a methyl group. So this is actually something like that. So find the parent chain. It's 4 carbons long. You've got a methyl group at carbon 2 and carbon 3. So you've got 2,3 dimethyl butane. So you already have your answer. You know that the only one of these 3 compounds that is not 2-methylpentane is going to be this one. But let's go through the other 2 just to double check. Okay, so again, notice you've got 2-methyl pentane. Okay, and then this one's actually kind of tricky. This one's actually kind of looks like this. Looks like it's going to be a different molecule, but it's actually still 2-methylpentane. Okay, next question. The difference in heat of combustion between compound 1 and 2 is found to be 17.2 kilojoules per mole. Question's asking you to redraw compounds 1 and 2, showing their chair conformations in their lowest energy conformations. Then compare between the 2 compounds, which one will have the highest heat of combustion. Okay, so the first thing here is going to be converting this bond line structure into a chair configuration, which is a little bit tricky on this molecule. Then analyzing these 3 cyclic structures. So in the first molecule, the cyclic structure that I have labeled B here is left in the chair conformation, whereas molecule 2, structure B, is forced into a boat conformation because of stereochemistry involved in the heterocycle here. So this carbon is forced up, whereas this guy here is kind of pushed down, locking you into this boat conformation. As we know, the boat conformation is going to be a little bit higher in energy because of those steric interactions in the chair conformation. So molecule 2 is going to have the highest heat of combustion. Okay, this slide just kind of shows the basics of the Coniglio-Prelog system of assigning priority to substituents connected to a chiral center. So this question says, determine the configuration R or S for all of the chiral centers in the following compounds. Okay, so I'm going to show you guys 2 ways to do this. One, I'm going to use my molecular modeling kit to show you how to do this. The other way I'm going to show you is essentially just being able to figure out the RS configuration without having a modeling kit. But I think that it's kind of helpful to see it with the modeling kit so you can kind of understand what you're looking at. So hopefully everyone can see me here. Let's see if I can make this bigger. Okay. So first molecule you're looking at is A, and that's something like this. Okay, so I rotate this guy out. You're looking at something like this. Okay, this is the carboxylic acid here, and then I'm holding this carbon in my bottom hand. That's the CH2OH. Okay, and so essentially, if I was to rotate this bond and this bond, I would now have my bond line structure. You can see that all of these alcohols can be on the exact same side now, which is kind of interesting. And this is kind of helpful for determining RS configuration. And so first, you'll notice that there's 3 chiral centers in this molecule. So I'm going to look at the first one here. So we know that we're connected, the central carbon is connected to 2 carbons, an oxygen, and a hydrogen. Hydrogen is going to be the lowest priority. Oxygen, since it has the highest molecular mass, is going to be the highest priority. Okay, so we're looking at this carbon right here. So you've got 1. Next, this carbon's connected to 2 oxygens. This carbon's connected to a hydrogen and 1 oxygen. So this is going to be 2. This is going to be 3. Hydrogen is going to be 4. So in this case, we're going 1, 2, 3. We're going clockwise. This is going to be R. Okay. So the next carbon here, again, hydrogen is going to be the lowest priority. Oxygen is going to be the highest priority. Next, we're analyzing the 2 carbons on either side. This carbon here is connected to an oxygen, hydrogen, another carbon. This guy here is connected to an oxygen, hydrogen, and another carbon. So look 1 carbon further. Next, we've got a carbon connected to 2 hydrogens and an oxygen. Next, we've got a carbon connected to 2 oxygens. So this is going to be number 2. So you've got 1, 2, and 3. Okay, so this guy's going counterclockwise, which would be S. Okay, and then lastly, we're looking at this bottom carbon. So obviously, again, oxygen is going to be the highest priority. Hydrogen is going to be the lowest. We know, so we got 1, 2. This guy, again, remember that's just representing the CH2OH on the bottom there. This is going to be priority number 3. So we're going to be going, again, clockwise. So this is going to be R. And then, again, if you want to convert back to the Newman projection, all you're going to do is just rotate these guys like that. And here is your Newman projection. So I'm holding the carboxylic acid again, and then the bottom is going to be the CH2OH. So I definitely recommend, if you guys have a molecular modeling kit, to mess around with it, see if you can practice a few of these before transitioning into just using pen and paper. Okay. So now I'll show you guys how to determine RS configuration without using the molecular modeling kit. So again, first notice how many chiral centers you have. We've got a chiral center here, got a chiral center here, and we got a chiral center here. So my strategy is to ignore the hydrogen, or the lowest priority. In this case, the lowest priority is hydrogen. In another circumstance, it could be some other atom, but ignore hydrogen and just deal with 1 and 2 and 3. Okay, so first chiral center here, this is going to be 1. Oxygen has the highest molecular mass. Then we're looking at carbon here and the carbon here. This guy's connected to 2 oxygens, whereas this guy's connected to 1 oxygen, hydrogen, and another carbon. So this is going to be number 2, making this 3. So we're going here in a clockwise direction, but you're going to reverse whatever you would think it is. So essentially, in this case, it would appear to be R. Really, it's an S. So I'm just reversing it, okay? And again, I'm just ignoring the 4th priority group. Okay. Next one, oxygen is going to be your highest priority. Then you're looking at a carbon, another carbon. This guy's connected to an oxygen, hydrogen, carbon. This guy's connected to an oxygen, hydrogen, carbon. So we're going to go one step further. We're going to look at this carbon here. This guy is connected to 2 oxygens. This guy is connected to 2 hydrogens and an oxygen. So this will be 1, 2, or I'm sorry. Let me take a step back here. So 1, 2, 3. So again, we're going clockwise. So it would appear to be an R configuration, but it's going to be an S, because it'll be the opposite. Okay. Oops. Hold on, guys. Okay, so next, we're looking at this carbon here. So again, oxygen is going to have the highest priority. Then, let me see if I can get my eraser back up. So oxygen is going to have the highest priority. Hydrogen is going to have the lowest. Then this guy is going to be 2, and this guy is going to be 3. So again, you're going in a clockwise direction, but it would be the opposite. So you're going to give it the S configuration. Okay, and lastly, look at compound C. Again, we've got 3 chiral centers. Look at the first one here. This is going to be 1, 2, 3, 4, nor 4th one. This appears to be an R. We know it's going to be an S. Okay, and this guy here, next chiral center, you've got 1, 2, 3, 4. This guy appears to be going counterclockwise, but we know it's going to be R, so it'd be the opposite of what we think. Here we got 1, 2, 3. This guy appears to be going clockwise, so it looks like an R, but we know it's an S. So here's the answers. Again, I definitely recommend, if you have a molecular modeling kit, take some time to practice and try to put all these molecules together and just be able to visualize the rotations and exactly what you're looking at here. Okay, next, this is kind of a little overview on some of the calculations that are involved with polarimetry. And so you could be trying to identify the specific rotation, the enantiomeric excess, or the percent of one enantiomer, RRS, that's in a mixture. Next question kind of is a good review of that. So we're asked, we've got a chiral catalyst that can be designed to favor the formation of a single enantiomer in a reaction where a new chiral center is formed. A redox reconfigurable copper catalyst is used that produced predominantly the S enantiomer when the copper 1 form of the catalyst is used, and the R enantiomer when the copper 2 form of the catalyst is used. Part A is asking you to draw the R and S products and identify the catalyst required to make each compound. And part B is asking you to determine which solvent is most efficient at producing selectivity between enantiomers by determining which compound gives the highest combination of percent yield and percent of the S enantiomer. Okay, so first we've got these two reactants. We've got this like dimethyl ester compound reacting with this substituted benzene compound to form a new carbon-carbon bond that also happens to be a chiral center. Now in this case, we only have one chiral center because if you're looking at this carbon, you would have two substituents that are the exact same, so you wouldn't be able to assign priority, and so there's no chiral center there. So you know you're going to have just one chiral center. And let's go to the next slide. Okay, so I've got both the R and S product drawn out. The S enantiomer is going to be produced when the copper 1 catalyst is present, whereas the R product will be produced when the copper 2 catalyst is used. So now we're asked to compare. Essentially, this reaction was performed using 3 different solvents as the variable to kind of analyze the ability of that solvent to produce certain percentage of that S enantiomer. So we're comparing toluene, tetrahydrofuran, and acetonitrile. And I'll show you how to do the calculation. Essentially, it's going to be 100 minus 24 divided by 2 plus 24, which is going to equal 62% S enantiomer. So that would be for toluene. Next, you've got tetrahydrofuran. So it's going to be 100 minus 48 divided by 2 plus 48, which will equal 74% S. And lastly, you've got acetonitrile, which would be 100 minus 72 divided by 2 plus 72, which is going to equal, let me see, 86% S. Okay, so now what we're doing is we're trying to find the solvent that produces the highest combination of percent yield, which is this information here, with the highest percent S enantiomer formed, which is this information here. So we see that acetonitrile has the highest percentage of S enantiomer, and it also has the exact same amount of percent yield as toluene. So these guys have equal amounts of percent yield. However, acetonitrile also happens to have a much higher percent S enantiomer formed. So the most ideal solvent to perform this reaction producing the S product is going to be acetonitrile, which is just a really common polar organic solvent. And if you wanted to figure out how much of the S product is formed, it's essentially just the other percentage there. So it would be 14%. So it'd just be 100 minus 86. You're going to get 14% R was produced. So they could kind of spin the question around and give you the data for the S and ask maybe about R if they wanted to be real tricky. Okay. So next, draw the bond line structures for the following combination compounds using wedges and dashes. Okay, so this one's kind of similar to the other Fischer projection question that we were going over. So essentially, one way to look at this is that all of these, this is actually going away from you, whereas these substituents on the sides are coming towards you. Okay. And so then what you're going to want to do is actually rotate these bonds here. Okay. And so what's going to happen is you're going to have all of these alcohol groups on the exact same side, like I can show you on the next slide here. So now you've got the alcohol groups all on the same side because you rotated these bonds here and here. Okay, and so you realize that you've got a meso compound, and this would not be optically active. You look at the next molecule, again, you're going to want to imagine rotating these bonds here and here. So again, you're going to get the alcohols on the exact same side. However, in this case, this is not going to be a meso compound. There's no plane of symmetry. Okay, the next molecule, again, you want to do the exact same thing. Rotate these bonds here and here. And again, you get the alcohols on the exact same side. So that's another way of kind of looking at these Fischer projections. Okay, question 8. Which of the following compounds is expected to be optically active at room temperature? So remember, in order for a compound to be optically active, it needs to contain a chiral center and not have a plane of symmetry. So compound A contains a plane of symmetry, so that will not be optically active. Compound B has a plane of symmetry as well. That will not be optically active. Compound B, if you rotate this top portion of the molecule, that sigma bond 180 degrees, you realize that you have this meso compound. Again, that would not be optically active. Lastly, you get to D and you realize that you have these methyl groups on the opposite sides of the molecule. There's no plane of symmetry. There's no symmetry there. This would actually be chiral. And so you're going to have these chiral centers, and since there's no plane of symmetry, this would also be optically active. So correct answer is D. Okay. So question number 9, this is analyzing some energy diagrams. And so first part of the question asks, which diagrams would correspond with a two-step mechanism? Okay, so when you're looking at these diagrams, you see that A only really has that one peak, B has 2 peaks, C has 1 peak, and D has 2 peaks. So you can kind of see that B and D are going to be your two-step mechanisms. So B and D. Okay. 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 Next part of the question asks, which diagrams would correspond with a one-step mechanism? That would be A and C. So ones just have one kind of hump in there in the diagram. Compare the energy diagrams, A and C. Which one has a larger activation energy? EA would be activation energy. So that would be kind of this guy here. Essentially, you've got your starting product, your starting material, and you're forming your product, okay? And this kind of hump here, this initial hurdle, that would be your activation energy, or the energy barrier that needs to be overcome in order for the reaction to proceed. You can see that just visually comparing it and see that C has a much larger energy barrier, so that's going to have a larger EA value. Okay, D is saying, again, compare diagrams A and C, which one would have a negative delta G value. Okay, so if you're looking at A, here's your starting material, and here's your final material. So your products have a much lower, more stable energy state than your initial starting material. And so what that means is that this would be an exothermic process, and this would correspond to having a negative delta G value. So this question is going to be A. If you look at diagram C, you notice that the starting material is pretty much at the same energy level as the final product. So there's actually really no change in energy there, and your delta G value would actually be close to 0 in that case, if not 0. So compare diagrams A and D, which one has a positive delta G value? So A and D, we already discussed A, we know that A has a negative delta G value. D, if you look at this one, your starting material is here, final products at a higher energy level. Okay, so this is going to have a positive delta G value. Okay, now part F is asking you to compare all 4 energy diagrams, determine which one exhibits the largest activation energy. Again, just a visual comparison. And it appears that D has that largest, sorry, my handwriting here is horrible. D would have appears to have the highest activation energy. G, which process will have a value, a K value that's greater than 1? So a K value of greater than 1 is going to be a process in which delta G is negative. So in that case, it's going to be, looks like both B and A would have a negative delta G value, and that's just based on the fact that the starting material is at a much higher energy state than the final product. So in this case, it'll be both A and B. Okay, and question part H is saying which process will have a value, a K value that's roughly equal to 1. We already talked about that. When delta G is 0, your K value is going to equal to 1. Delta G is 0 when the starting material is roughly at the same energy level as the final product, which is in the case of C. So C would have a K value somewhere around 1. Okay, question 10. What is a reaction order? In this case, draw the arrow pushing mechanism, and then would you expect the reaction to be endothermic or exothermic? Okay, so first we're looking at the reaction here. We've got nucleophile here coming in, doing a backside attack, SN2 style. We're going to have a loss of leaving group. Bromine, it's a halogen, has nearly a full octet, so that's a good leaving group. It's a relatively stable anion. And then you get your final product here that shows an inversion of stereochemistry. the stereochemistry is not shown in this case, but it's expected that the stereochemistry would undergo an inversion. And then we're looking at the rate here. The rate is based on the nucleophile and it's based on the substrate. So this is a second order reaction. Okay, and then lastly, we're looking at the energy diagram. We're trying to determine whether this is an endothermic or exothermic process. So here's our starting material, and it corresponds to a little bit higher of an energy than the final product, which is somewhere around down here. Okay, so what happens is as this reaction undergoes, and you have your, I can draw out the transition state here. Okay. Okay, so there's your transition state. And okay, what happens is the energy, there's a difference in energy between the starting material and the final product, and that difference in energy is going to be released as heat, making this an exothermic process. So you see that your starting material is at a higher energy than your final product, and that difference, the difference in energy there is released, in this case, is heat. Okay. Question 11, draw the curved arrows and label the steps as loss of leaving group, carbocation rearrangement, proton transfer, or nucleophilic attack. Okay, so in this case, again, you're really just asked to draw out the curved arrow mechanism. You're not going to be expected by any means to propose a mechanism for a conversion of this starting material to this product here. You'll learn that in your second semester of organic chemistry. But in this case, we're just going to be then drawing curved arrows. Got a proton transfer here. Then have a nucleophilic attack. Oops. Sorry about that, guys. Okay. Nucleophilic attack here. Okay, then you have another proton transfer. Okay, another proton transfer here. This guy is going to be loss of leaving group. This is kind of cool. This is like a little intramolecular nucleophilic attack. These electrons go up. And let me see, what else can we do? Proton transfer here. Okay, and that's it. So pretty much the point of this question is just to be familiar with these different transitions, nucleophilic attacks, loss of leaving groups, proton transfers. You guys want to be familiar with kind of drawing those curved arrows, and then eventually you'll get to the point where you'll be asked to actually propose a synthesis. Okay, next question. Identify all chiral centers and draw possible stereoisomers. So first thing, let's take a look. How many chiral centers do we have? These guys are all sp2 hybridized. This guy can't be a chiral center, 2 methyl groups. Here's a chiral center. Here's a chiral center. And that appears to be it. So we just got 2 chiral centers. Now, how can we possibly figure out how many stereoisomers we have? Well, there's a really easy mathematical relationship. 2 square root n, where n is the number of chiral centers. So in this case, we would have 2, 2 chiral centers equals 4. So we got 4 different possible stereoisomers. In this case, these guys are going to be enantiomers here, whereas these guys will be your diastereomers. Okay. So pretty straightforward. Okay, next, draw a relative energy diagram showing the conformational analysis of 1,2-dichloroethane. Use Newman projections to illustrate the staggered and eclipsed conformations that correspond to each potential energy level. Okay, so keep in mind that the energy gap between the different conformations of this dichloroethane are all just relative to each other. So there's no actual numerical energies associated with this y-axis. So first, draw the molecule. So we got something like this. Okay, that's just the bond line structure. Then let's draw this out in the Newman projection. Okay. So here's your Newman projection. Now notice these chlorines are anti to each other. So that's going to be your lowest energy conformation. And what you're going to want to do is do a 60-degree rotation here. Okay, so have it all drawn out here. So you've got these chlorines, again, anti to each other. So that's going to be your most stable conformation. You've got the staggered conformation here. And so this guy's going to correspond to the lowest amount of energy, and these chlorines are 180 degrees apart. Then you're going to want to do a rotation. I'm going to rotate the top front part of the molecule. And so you're looking at this. These guys are now in the eclipsed conformation, which will be associated with a little bit higher amount of energy. And so then you're going to do another 60-degree rotation, puts you back in the staggered conformation. Chlorines are a little bit closer together now, so going to be associated with a little bit more energy than the initial configuration, but not much. You're going to then want to do another 60-degree rotation that puts you eclipsed again. Now you've got these chlorines right on top of each other. That's going to be actually the highest energy point in this for this molecule here. So then you do another 60 degrees. You now have the staggered conformation, and these two here will be equal to each other in energy. Then you again do another 60-degree rotation. And now you can see that these two conformations are equal. And then finally, you do another 60-degree rotation. You now have these chlorines back in the anti position, and it's a little bit more stable now. So again, keep in mind that these, the energy associated with these conformations are all relative to the highest energy conformation, the lowest energy conformation. And you just want to keep in mind that you're doing 60-degree rotations each time, and that when you draw these out, the molecules appear to be kind of on an angle from each other, but you're going to want to imagine that they're almost directly on top of each other. Okay. Question 14, draw both chair conformations for trans 1,4-diisopropyl hexane and cis 1,3-diisopropyl hexane. Then you're going to want to compare the two molecules and identify the most stable chair conformation for each molecule. Okay, so I drew out the bond line structure for the first molecule, and then I converted it to a chair conformation. Now, in this case, you've got these two isopropyl groups that are axial, and they're going to account for those 1,2 diaxial interactions. So this guy is going to be associated with a little bit more higher energy level, whereas when you do the chair flip, you now have these isopropyl groups in the equatorial position. There's going to be less of those 1,3 diaxial interactions, and this guy will be your more stable conformation. Again, the second molecule, you draw out the bond line structure, then convert it to a chair conformation. You notice that the first conformation drawn here counts for those quite a bit of steric interactions here between these two isopropyl groups. So this guy is going to be associated with a higher energy level. And then when you do a chair flip, you now have these isopropyl groups equatorial, and there's going to be less of those steric interactions. And so again, this conformation will be the more stable conformation. Okay, 15. This slide just shows you kind of an overview of the 6 common radical patterns that you can keep in mind when you're analyzing mechanisms for radical reactions. So you've got homolytic cleavage. Essentially, you've got 2 halogens that are splitting apart to form 2 halogen radicals. And so homolytic cleavage is essentially the opposite of coupling. So then you've got addition to a pi bond. So you've got a radical, a halogen radical that's interacting with a pi bond. It's double bond here. That's forming a new sigma bond. So you're losing that pi character and you're forming a new sigma bond. Okay, and so that's going to be essentially the opposite of elimination, where you're taking this sigma bond and you're forming a new pi bond and you're having this halogen radical now. And then you've got hydrogen abstraction, where you've got a hydrogen radical that's going, or I'm sorry, a halogen radical going and stealing a proton here, leaving radical on this carbon. And then you've got vice versa, halogen abstraction, where you've got this R group that's going to take a halogen, forming a halogen radical. Okay, this slide just kind of gives you an overview of, I wanted to point out this reagent here, N-bromosuccinimide, or abbreviated NBS. This can be used to help eliminate competing ionic addition reactions in allylic bromination. And the way it does that is by providing just a single bromine rather than 2 bromines. And so it's a little bit more controllable. So I just wanted to point that out. And then the bottom part of the slide here shows you just a bromination reaction, where you've got this alkene reacting with molecular bromine to form this halogenated compound. But I don't think you guys go over that too much until I think chapter 8. Okay, identify the products of the following radical reactions. So essentially what you're trying to do is just figure out the most ideal spot for the halogen to be placed. So in this case, bromine is going to be placed here because that tertiary position is more stable than the primary. For part B, you've got iodine. You would think that the exact same thing could happen, right? You'd think that you could just put this iodine here, but if you go to table 6.1 in your textbook, that has a list of the delta H values. And if you were to analyze the bonds that are broken and the bonds that are formed, you would get a positive delta H value, and you'd realize that this reaction is not thermodynamically favored. So this is not going to actually occur at all in most cases. So part C, chlorine and light. This is actually going to produce possibly several different products. So you could have chlorine here, and this would be racemic because you're forming a new chiral center. You could have your chlorine here, or you could have your chlorine in the primary position. So you could get a combination of those different products. For D, in this case, you haven't learned any reactions that would allow you to place a halogen on, or any substituent for that matter, on a benzene ring directly. However, in this case, you have this allylic position and the bromine's able to add there. It's actually a fairly stable position because of the resonance stabilization. And so in this case, this would be your only product that's formed. For part E, you actually have to draw out some resonance here. So actually have in this case, you could draw some resonance structures. Okay, that will show you that you could have two possible products. Which would be these two. Okay, and so this would be like something like that. Okay, and then for part F, you're gonna have your bromine placed there. And the reason why is because if you look at the other side, that carbon's completely occupied. You've got 3 methyl groups and then this other carbon coming off of it. So the only location is going to be the tertiary component there. You could get it in the primary position, but the tertiary would be more stable. Okay. Question 18. This is kind of a tricky one. A carbon-carbon bond is made up of 1 sigma bond and 1 pi bond. These 2 bonds together have a bond association energy of 607 kilojoules per mole. Use this information to estimate the delta H value for the conversion of compound 1 into compound 2. Okay, so what we have to do is analyze the bonds that are being broken, the bonds that are being formed. So you're looking at really just this part of the molecule. And you notice that you have this pi bond converting into a sigma bond, okay? So this would be addition to a pi bond. If you're thinking about those 6 different common patterns of radical reactions. So essentially you've got this guy here. I'm going to draw out the hydrogens being broken, but just the pi component. You also have an HBr molecule, that bond's being broken as well. Broken, and the bonds that are being formed are these guys here. You've got a new sigma bond being formed and a new hydrogen, carbon-hydrogen bond being formed. So the first part formed. Okay, so the first part of this question is essentially just going to be figuring out which bonds are broken and which bonds are formed. Once you figure that out, you can correlate those components that are being broken and formed to an energy, an amount of energy that you can find on this table in chapter 6.1. And in this case, I actually got this table just off of Google, but if you take it directly from your book, it's actually a little bit different, so I apologize. But first, you've got this pi bond that's being essentially removed, and you're forming this sigma bond. So you can't actually find that on this chart, unfortunately. We're going to have to use this equation here to calculate that. So we know that the bond association energy, according to the question, is 607 kilojoules per mole, right? And so we're trying to solve for bond association energy of just the pi bond. We know the bond association energy of the sigma bond, according to this chart, you can find that that is you think? Let me see here. That guy would be 365, or 356 kilojoules per mole, and that could be found so unfortunately that guy's not shown here. That would be something like this. Let me plug my computer in here real quick. Okay, so that would look something like this, CH3, CH2, and then this is the bond, CH3, which would equal 356 kilojoules per mole. Okay, and that's found on this chart here, 6.1 in the textbook, but it looks like the chart that I found on Google doesn't actually have that on there. So I apologize, but if you want to practice this problem again, take a look in your textbook, table 6.1, all the way on the bottom left-hand corner. It's going to be 356 kilojoules per mole. Okay, so now it's just basic arithmetic. When you solve for the bond association energy of the pi bond only, you get 251 kilojoules per mole. Okay, and that is what we're going to use in our final calculation for the delta H. So we know that that's going to be this bond that's broken here. So 251. And since that bond's being broken, it's going to be a positive value. So 251 plus, we've got this HBr sigma bond that's breaking. We can find that on the chart here probably. And that's down here, 368. Again, that's plus 368. Okay, and then next, we've got these bonds that are being formed. So we got a new carbon-hydrogen bond being formed. Okay, so that's 397, which is found here. There we go, 397. That's going to have a negative value. Okay, and these are all kilojoules per mole, by the way, but I just didn't draw it out. And then lastly, we've got a carbon-bromine bond that's being formed. Okay, so that's going to be 285, and that's right here, negative 285. Okay, so now when you add these all up, you got 251 plus 368 minus 397 minus 285, that gives you negative 63 kilojoules per mole. That's going to be your final delta H for the conversion of this molecule to this molecule via the radical bromination reaction. Okay, one more problem. This guy here, propose a plausible mechanism, initiation, propagation for the ring closure reaction. So this is a key component to paclitaxel, which is a very well-known chemotherapeutic agent. So essentially, this question is just asking you to identify these different radical reactions according to those 6 key patterns that we pointed out in a previous slide. So here we've got a radical reacting with a double bond to form a new sigma bond. Okay, that's addition to a pi bond. Okay, next we've got another radical reaction reacting with a double bond. So that's again going to be addition to a pi bond. Oops. Okay, now we've got this radical reacting with a halogen. So this is going to be a halogen abstraction. Okay, and now you get your final product. Cool. So I hope this helps you guys prepare for your exam. If you guys have any questions at all, feel free to email me. Hope you guys all stay safe and good luck.